This video tutorial covers giant covalent structures and explains why they are solids with high melting points and high boiling points. It also compares different types or different allotropes of carbon. So this will include diamond, graphite and C60 fullerenes. Why does diamond have a high melting point? Pause the video, see if you can answer the question, and then continue. If you're not sure, I'll show you a series of images which will hopefully help you. So the first one is a picture of Shrek, and what is he? This is a diagram trying to represent a type of bonding. You can see a shared pair of electrons here, and obviously the attraction is between a shared pair of electrons and the bonded atoms, nuclei. This is a very large number. The next two pictures are trying to represent something, as in what is the chair, and also something we might describe someone as if they have powerful biceps. Then the last image is a picture, or penultimate image rather, is a picture of the sun, which contains or gives out or has lots of something. And finally, talking about something being broken. So firstly, Shrek. What does the image of Shrek represent? It represents that diamond has a giant something structure, covalent structure with what sort of bonds, how many bonds, with lots of strong covalent bonds, which will require what? A large amount of energy to obviously break the bonds. Really important to learn this definition and try to be sort of, relatively speaking, as close to this definition as you can be. Why is diamond hard? Pause the video, see if you can answer the question, otherwise you'll be able to shortly see a sentence with gap fill. So why is diamond hard? As in, why is it sometimes, or why is it so hard it's actually used for drill tip bits? So again, we've got Shrek, so it must remind us that we've got a giant structure. Other things we could also think about is, this is a three-dimensional drawing, as in all the atoms are joined together in a massive lattice going in every single direction. That's showing a tetrahedron. So it's a giant three-dimensional tetrahedral lattice. Then we have to think about something to do with carbons being bonded. Here's a picture of carbon. We can see it's formed 1, 2, 3, 4 bonds, and it's joined to 4 other carbons. So every carbon is covalently bonded to 4 other carbons. Then we have to think about how strong the bonds are. They're strong, so it's got some covalent bonds which are very strong. Is diamond a good conductor of electricity? Diamond is not a good conductor of electricity. It's a poor conductor of electricity. And why is this? Because if you think about the diagram showing carbon, it's formed 4 bonds. So all the outer shell electrons, all 4 outer shell electrons are used for bonding, and carbon has formed 4 covalent bonds. For electricity to be conducted, we would either need mobile delocalized electrons such as in metals, or ions such as in ionic compounds for electricity to be carried through a substance. Why does graphite have a high melting point? Pause the video and see if you can answer it. You should also be able to do it because this is exactly the same question as why does diamond have a very high melting point? So again, it's got a giant covalent structure with lots of strong covalent bonds which will require a large amount of energy to break the bonds. Is graphite a good conductor of electricity? Pause the video, see if you can think about what the answer might be, and then push play. So graphite is sometimes used as electrodes during electrolysis. So it is a good conductor of electricity from our practical experience. Why is this? If we look at the diagram, it's showing a little bit of a graphite layer. We can see each carbon is bonded to 3 other carbons. So each carbon has bonded to 3 other carbons with covalent bonds, resulting in what? here's a little electron which isn't actually in one specific place, but it's a delocalized electron. So it's got one delocalized electron per carbon. And what can the electrons do? They can obviously move throughout the structure. Why is graphite used as a lubricant? The following diagram may help. So graphite exists in layers. And what can these layers do? They can obviously slide over each other. If you imagine a stack of paper on the floor, if you stood on it, they could all slide over each other. And then what's between the layers? There are only weak forces of attraction between layers. It is not weak intermolecular forces. Inter means between, molecular means between, so intermolecular means between molecules, and it is not separate molecules, it's merely layers of the same giant structure. Why is graphite soft? The following images should hopefully help. Pause the video, see if you can answer the question. So graphite has layers which can slide over each other with only weak forces of attraction between the layers. Obviously, if it was forming 4 bonds like in diamond, the layers wouldn't be able to slide over each other. And this is because each carbon is only bonded to 3 other carbon atoms in its layer. The next thing we're going to have a look at is why does C60 have a low melting point? If we look at the formula, it shows us there are 60 carbons joined together, so this means it must have a simple molecular structure. Here are some pictures which will hopefully help give you some inspiration. If you imagine pulling both ends, this link here would be the one which goes, so it's the weak link in the chain. So this is trying to remind us that here we've got forces of attraction, but it's not strong covalent bonds, but weak intermolecular forces of attraction. And what's it between? Molecules. So the intermolecular force of attraction are obviously weak, and therefore how much energy do we need? This is showing what the amount of energy we need. You can see that's giving off a little bit of energy compared to that, so only a little energy is needed to overcome the weak forces of attraction. I hope that was a helpful summary and recap of the different allotropes of carbon and also why diamond and graphite have high melting points.